1803, and ruthenium, Claus in 1844, have been given careful consideration by chemists. Platinum is used extensively in making chemical apparatus, especially crucibles and stills, and osmium and iridium have recently come into use as filaments for incandescent lamps. About 15 years ago, the number of the chemical elements was enlarged by two gases of great theoretical interest, argon and helium. As early as 1785, Cavendish had noticed that a residue of about 0.6% remained when the nitrogen and oxygen were removed from air, and in 1894, Rayleigh discovered that nitrogen from the atmosphere was 0.5% heavier than nitrogen prepared chemically. Rayleigh and Ramsay then prepared large quantities of this atmospheric residue and found it to be a gas different from nitrogen. They called it argon, from the Greek argos, for lazy. Helium was discovered by Ramsay in 1895 in the mineral cleveite. It had already been found to exist in the chromosphere of the sun by Janssen in 1868, and his observations were confirmed by Franklin and Lockyer. Helium, primarily obtained by heating cleveite with sulfuric acid, and since found in small quantity, often together with argon, found in the minerals uraninite, malacone, etc., as well as in the gases from some mineral water springs, is like argon, inert and indifferent. Up to now, in spite of persistent effort, no compound of either argon or helium has been prepared. And further, although many diffusion experiments with both gases have been carried out, with the object of seeing whether they were really elementary, the densities of both have remained unaltered. For example, it has been found impossible to subdivide them by diffusion into two or more components. From the ratio of the specific heats at constant volume and constant pressure, it follows that the molecule and atom are identical in both argon and helium. For example, that the gases are monatomic, and this applies also to the more recently discovered gases of the air, krypton, neon, and xenon. These were separated from liquid air in 1898 by Ramsay and Travers. The atomic weights of these gases and the proportions in which they are present in the air are as follows. Helium, atomic weight, 4. 1 part by volume in air, 2,450 volumes. Neon, atomic weight, 20. 1 part by volume in air, 808 volumes. Argon, atomic weight, 39.9. 1 part by volume in air, 105 volumes. Krypton, atomic weight, 81.8. 1 part by volume in air, 746,000 volumes. Xenon, atomic weight, 128. 1 part by volume in air, 3,846,000 volumes. Since the interest attached to these gases has been recently augmented by the discovery of Ramsay and Soddy that radium emanation eventually changes, at least in part, into helium, and since Ramsay has shown that when the radium emanation decays in the presence of water, neon is produced, and that argon results when the decay takes place in the presence of water containing a copper salt in solution, the radioactive elements may be conveniently referred to here. Henri Becquerel found in 1896 that compounds of uranium spontaneously and continuously emit some radiation, which, among other properties, has that of making air a conductor of electricity. This effect, the quantity of which can be determined with great accuracy, was used by Madame Sklodowska-Curie to measure the amount of radiation produced by various compounds of uranium and of thorium, which latter had been found by Schmidt to emit the same kind of radiation. She subsequently tested a large number of rocks and minerals and found that certain minerals which contain uranium and thorium, for example pitchblende, oxide of uranium, chalcolite, double phosphate of copper and uranium, possess radioactivity much greater than that theoretically due to the amount of uranium present. Madame Curie therefore inferred that it appeared probable that if pitchblende, chalcolite, etc., possess so great a degree of activity. These substances contain a small quantity of a strongly radioactive body, differing from uranium and thorium, and the simple bodies actually known. I thought that if this were indeed the case, I might hope to extract this substance from the ore by the ordinary methods of chemical analysis. The investigation was consequently pursued, and with the assistance of her husband, Pierre Curie, and Gustave Beaumont, Madame Curie commenced the laborious treatment of the residue remaining after the extraction of the uranium from pitchblende, a large quantity of which had been placed at her disposal by the Austrian government, and finally separated the salts of radium in 1898. While endeavoring to isolate radium, Madame Curie discovered polonium, and other investigators, de Biernet, Gazelle, Markwald, and Hoffman, have given the names of actinium, emanium, radiotellurium, and radio-lead to similar substances, the two last being possible products of the spontaneous change in radium. Among those who have worked with success upon the problem of radioactivity, Elster and Gettel, Rutherford, Soddy, and Ramsay may be mentioned here. Radium maintains a temperature 1 or more degrees above that of the atmosphere, injures the eyes, and disorganizes the flesh when kept long in contact with it. Its peculiar properties have been explained in various ways. The most plausible suggestion is that atoms of high atomic weight slowly disintegrate into ultimate corpuscles or particles, and that this decomposition is attendant with the development of great energy. The successive disintegration of the radium atom, as exemplified by the disintegration of products, is shown in the following table, which represents, according to Ernst Rutherford, the complete radium series as at present known. Radium, radiation emitted, alpha particles. Period, 2,000 years. Range of alpha particles in air at normal pressure, 3.5 centimeters. Radium emanation, radiation emitted alpha particles. Period, 38 days. Range of alpha particles in air at normal pressure, 4.3 centimeters. Radium A, radiation emitted alpha particles. Period, 3 minutes. Range of alpha particles in air at normal pressure, 4.8 centimeters. Radium B, radiation emitted beta particles. Period, 26 minutes. Radium C, radiation emitted alpha and beta particles, gamma rays. Period, 19 minutes. Range of alpha particles in air at normal pressure, 7.06 centimeters. Radium D, radiation emitted unknown. Period, 40 years. Radium E, radiation emitted unknown. Period, 6 days. Radium F, radiation emitted beta particles. Period, 4.5 days. Radium G, radiation emitted alpha particles. Period, 140 days. Range of alpha particles in air at normal pressure, 3.86 centimeters. It appears that uranium is the source of radium, and Boltwood has recently announced the immediate parent of radium, ionium. Radium represents barium chemically, and according to Madame Curie and Thorpe, it has an atomic weight of 226.5. Several observers have demonstrated that it possesses a characteristic spectrum, and consequently, notwithstanding its disintegration and peculiar conduct, radium is regarded as a chemical element. Owing to an affidation among chemists to recognize a body as a chemical element when, under proper conditions, it possesses a definite atomic weight and exhibits a spectrum containing characteristic and novel lines. In 1823, Mitscherlich discovered the existence of sulfur in 2 different crystalline varieties, rhombic and oblique, and a third variety, a plastic form, was also known. Frankenheim learned that by heating and cooling, these varieties could, at definite temperatures, be converted into one another, and in describing these phenomena, the term isomerism was employed, to which, however, Berzelius published an objection in 1841. To quote from his Jahresbericht for that year, I feel compelled to call attention to the fact that the word isomerism, which is applied to different substances composed of an equal number of atoms of the same elements, is not compatible with the view as to the cause of the different properties exhibited by the various modifications of sulfur, carbon, silicon, etc. While the term still lends itself to the expression of the relation between ethyl formate and methyl acetate, it is no longer suitable in the case of simple substances which assume different properties, and it might be desirable to substitute for a better chosen term, for example, allotropy or allotropic modifications. In accordance with these views, there can be more than one cause for that which we call isomerism, namely 1. Allotropy, in which case the difference between the sulfides of iron is due to the fact that they contain different modifications of sulfur. 2. Differences in the relative position of the atoms in the compound, of which the two kinds of ether, ethyl formate and methyl acetate, are so striking a proof. 3. A combination of 1 and 2. Since then the term allotropy has been in constant use, and numerous allotropic phenomena have been observed, particularly among the non-metals. The allotropism of carbon was the first observed example, 1773, and its modifications exhibit marked points of difference, for instance, comparing diamond and graphite. Carbon, diamond, crystallographic system, cubic, optical properties, colorless, transparent, high refractive index, mu equals 2.417. Chemical and physical properties, non-conductor of heat and electricity, not attacked by oxidizing agents, ignition temperature 760 degrees to 875 degrees. Specific gravity 3.52. Hardness 10. Carbon, graphite. Crystallographic system, hexagonal or oblique. Optical properties, opaque. Chemical and physical properties, good conductor of heat and electricity, oxidized to graphitic acid, ignition temperature 575 degrees and above. Specific gravity 2.25. Hardness 1. When amorphous carbon, coal, peat, lampblack, etc., and diamond are heated, they pass into the graphitic variety, and graphite is now produced in large amounts by heating carbon to a high temperature, 4,000 degrees Celsius, by an alternating electric current. Henri Moissan, 1852 to 1907, an eminent French chemist, succeeded in preparing synthetic diamonds by dissolving pure sugar charcoal in molten pure iron and suddenly cooling the mass by plunging it into water, and 3 English chemists, Sir F. A. Abel, W. H. Noble, and Sir William Crookes, obtained diamonds by exploding some of the high explosives and steel bombs, the liquid carbon produced, crystallizing as it cooled. However, no diamonds have thus far been produced of commercial size or amount. The most peculiar, as well as noteworthy, example of allotropism is afforded by the conversion of oxygen into ozone. Ozone was first noticed by Van Marum in 1785 in electrified air. In 1840, C.F. Schonbein called attention again to this substance, discovering its oxidizing action, and showed that it was produced in the electrolysis of water and in the slow combustion of phosphorus and sulfur. He gave it the name ozone, which means a smell. The investigations of Marillac, de la Rive, Becquerel, Tate, Fremy, Andrews, and Brodie have proved it to be modified oxygen. Its density was determined by Surret in 1860. The latter, and before him Andrews, proved that the ozone molecule contains 3 atoms of oxygen, while a molecule of the latter is made up of 2 atoms. Ozone is now used in the sterilization of water. Among other allotropic modifications, those of selenium and phosphorus are of interest. Berzelius investigated the allotropes of selenium, and those of phosphorus were studied by Berzelius, Schroeder, Hittorf, and Schenck. Schroeder discovered the red variety in 1845, and Hittorf found that it could be transformed into a metallic modification. Several additional allotropes of sulfur have been discovered in late years, and the fact that many metals can exist in allotropic forms has been clearly demonstrated. For example, colloidal gold, silver, platinum, and mercury. The list of the compounds of the elements was greatly extended from the time of Lavoisier, particularly with the discovery of new acids and the growing knowledge of the different basicity of the various acids. It is important to mention some of the discoveries of moment. In 1818, one of the most interesting of inorganic compounds was discovered by Thénard. He proved that water is not the sole oxide of hydrogen, but that another, peroxide of hydrogen, but which he termed oxygenated water, may be prepared. This compound plays a prominent role in many processes of nature and is now prepared in quantities by treating barium dioxide with sulfuric acid for disinfecting and bleaching purposes. The list of the halogen acids was completed prior to 1820. Gay-Lussac and Ballard studied hydriodic and hydrobromic acids. The former, Davy and Faraday, investigated hydrochloric acid, while Thénard, Gay-Lussac, and Berzelius contributed greatly to an intimate knowledge of hydrofluoric acid. In 1869, Gore and Nicholas continued the investigation of anhydrous hydrofluoric acid, and the latter lost his life through its action. Gore and Fremy established its composition, but as before mentioned, the element fluorine was not isolated until 1886. The oxygen compounds of chlorine, iodine, and bromine have been given much attention since the commencement of the 19th century. The work of Gay-Lussac on chloric acid, Ballard on hypochlorous acid, Milan on chlorous acid, and Davy and Stadion on chlorine peroxide was exceedingly valuable and led to researches which firmly established the composition of these bodies. The oxygen compounds of iodine received careful attention in the hands of Davy and Magnus, and the latter discovered iodic acid, the principal compound of that halogen. Following Gay-Lussac's discovery of hyposulfurous acid in 1813 and dithionic acid in 1819, little attention was given to the compounds of sulfur and oxygen until the fourth decade, when the thioacids, which contain more sulfur and are more closely related to sulfuric acid, were recognized. More recently, the early known oxides of sulfur, sulfur dioxide and sulfur trioxide, have received several additions in sulfur sesquioxide, sulfur tetroxide, and sulfur heptoxide. Sulfuric acid, the most important of all chemicals, is used in enormous quantities in the industries, and its manufacture has been immensely developed. Over 2 million tons were used in the United States in 1908. The very poisonous compounds of hydrogen with phosphorus, arsenic, and antimony, phosphine, arsine, and stibine, were given considerable attention during the first and second decades of the modern period. Phosphine, or hydrogen phosphide, discovered in 1783 by Gendebray, and its composition was studied by Davy. Rose continued its investigation at a later date. Arsine was prepared in a pure state by Soubrain. Gellin fell a victim to its toxic action in 1815. Phosphorus and phosphoric acids were known to Lavoisier, but their constitution was not established until a much later period. It was upon the relations which Gay-Lussac, Strohmeyer, and Graham found existing between the ortho, pyro, and metaphosphoric acids that Liebig founded his theory of polybasic acids, which marked such an important step forward in chemistry. The important compound, hydroxylamine, which may be regarded as ammonia, in which a hydrogen atom has been replaced by hydroxyl, OH, was discovered by Lawson in 1865. It has led to a knowledge of many remarkable organic compounds. Similarly, the analogous compound, hydrazine, which was first prepared by Curtis in 1887, has entered into the preparation of a series of interesting compounds, for example, the hydrazones and hydrazides. It is an exceedingly powerful reducing agent. Of the simple carbon compounds, the greater number were discovered in the first decade. Carbon disulfide, which was accidentally discovered by Lampadius in 1796 while heating pyrites with coal, was accurately examined by Vauquelin in 1812. It is now prepared in an electric furnace by conducting sulfur vapor over heated carbon and finds extensive use as a solvent. Carbonyl chloride, or phosphine gas, was discovered by Davy in 1811, and carbon oxysulfide by von Than, quite recently. The compounds of carbon with certain metals, carbides, are now of great technical importance. In 1808, Davy discovered potassium carbide, the first described in chemical literature, and in 1862, Wöhler prepared calcium carbide, now one of the most important on account of its use in the generation of acetylene and in the manufacture of calcium cyanamide, a new constituent of fertilizers. Calcium carbide has, since 1894, been prepared by fusing limestone and carbon together in an electric furnace. Before closing this brief resume of some of the advances made in the knowledge of chemical compounds, mention must be made of the metallic peroxides, hydrides, and nitrides. Sodium peroxide, which was discovered by Gay-Lussac, is now used extensively under the name ozone as a bleaching and oxidizing agent, and calcium peroxide, discovered by Gay-Lussac and Thenard, is used in dentistry. The discovery of the hydrides belongs to the present day. Among the most important of these is calcium hydride or hydrolyte, which is used for generating hydrogen. The metallic nitrides, as magnesium, calcium, boron, and lithium nitrides, have only lately been investigated carefully, but may become of great importance. Numerous important chemical and physical facts were learned concerning the gaseous bodies, especially during the second, third, and seventh decades, and the experiments which were conducted with a view of liquefying gases are of the highest import, more particularly with regard to the production of liquid air and its application to researches at low temperatures. The experiments of Davy and Faraday, in which the gases were generated in curved, closed glass tubes and cooled to about -20 degrees Celsius in a freezing mixture, resulted in the liquefaction of all the common gases, with the exception of hydrogen, nitrogen, oxygen, methane, carbonic oxide, and nitric oxide. In 1834, Thilorier liquefied carbon dioxide in considerable quantities and obtained the solid. He was the first to operate on a large scale, and subsequent investigators made use of many of his observations. Between the years 1844 and 1855, Natterer studied the relationship of pressure and volume over wide ranges of pressure, and in 1852 he exposed hydrogen to a pressure of 2,790 atmospheres, but was unable to effect its liquefaction. It was only in 1877 that Raoul Pictet and Louis Cailletet succeeded, almost simultaneously, in liquefying the majority of the so-called permanent gases. Their success was due to a recognition of the fact that reduction of temperature was necessary as well as pressure, but it was not possible by the aid of the methods and appliances which they employed to obtain the liquids in large quantities and to determine their physical constants. This was accomplished by Wroblewski, a chemist in Krakow, and he had Olszewski first obtain quantities of oxygen and nitrogen in the liquid state and describe many of their properties. These two investigators share with Dewar, an English chemist, the honor of having first devised practical methods for the production of liquid air in quantity. And in 1896, C. Linde in Germany and W. Hampson in England constructed technically efficient forms of apparatus for producing liquid air. Liquid air has not as yet, however, found any technical application upon a large scale. Nearly pure oxygen is obtained from it very cheaply, and the attempt has been made to apply it in the manufacture of explosives, but so far, liquid air has achieved the most important results in chemical research. In the first place, it must be mentioned that Dewar, by its aid, has succeeded in liquefying hydrogen and in obtaining air, oxygen and hydrogen in the solid state, and that in doing so he has achieved almost everything that can be done in this direction. However, he is at present attempting to reach the so-called absolute zero. The results that have been obtained by means of this agency with respect to the discovery of the noble gases are of greater importance. Since these have been described, it only remains to be stated that Ons, in his cryogenic laboratory in Leyden, has recently announced that he has liquefied helium and that it boils at negative 268.5 degrees Celsius. End of section 18.
Section 19 of The Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in May 2018. The Science History of the Universe, Volume 4, edited by Francis Rolt Wheeler. Chemistry. Chapter 15. Atomic Weights and Periodic Law, Part 1. In a preceding chapter, an attempt was made to trace the early development of the atomic theory, and later it was shown how this theory became a necessity for the development of organic chemistry. It had fallen into disfavor because of the difficulties encountered by Berzelius and others in distinguishing between atoms and molecules, but much light was thrown upon this and other matters as the chemistry of the compounds of carbon was better understood, and the fact that the dominant doctrine of the new chemistry quietly assumed the truth of Dalton's theory in all its important particulars was reflected upon the older chemistry, so that this great theory became the basis for it all. The old confusion between atoms and equivalents was not entirely done away with until after Frankland's investigations of the organometallic bodies. Yet, in 1846, Laurent had clearly distinguished between atom, molecule, and equivalent, and his definitions are still current. He stated that the atom of M. Gerhardt represents the smallest quantity of a simple body which can exist in a combination. My molecule represents the smallest quantity of a simple body which must be employed to perform a chemical reaction. This definition of a molecule was employed until quite lately in general, but in 1888 Lothar Meyer pointed out that it was insufficient. Gerhardt defined equivalent as follows, quote, "According to our views, the conception of equivalent implies that of similarity of function. It is known that the same element can play the part of one or other of several very different elements, and it may happen that to each of these different functions corresponds a different weight of the first element." End quote. 7 years previously, in 1842, when he had not arrived at a clear distinction between equivalent and atomic weight, Gerhardt had doubled the equivalents of carbonic acid and of water, and in 1843 he followed this up by doubling the values of the symbol weights used by French chemists. H equals 0.5, O equals 8, C equals 6, etc., rendering them thereby identical with Berzelius's atomic weights. The reasons for this change were derived from the study of chemical reactions. He found that the amounts of water, carbonic acid, ammonia, and sulfurous acid evolved in the interactions between the quantities of organic compounds represented by the formulae assigned to them on chemical grounds were always 2, or multiples of 2, equivalent weights of H2O, CO2, SO2, when H equals 0.5, O equals 8, C equals 6, S equals 16. Both Gerhardt and Laurent expressed sound views on the selection of atomic weights. They recommended the choice of such of these as were in agreement with the requirements of the law of isomorphism, the law of Avogadro, and the law of heat capacity, and which above everything are chemically adequate. However, apparently the chemical public was not yet ready for the change. In his great textbook on organic chemistry, the publication of which was begun in 1853, Gerhardt retained Gmelin's equivalent weight notation. He is reported to have said in private conversation that unless he had done so, no one would have bought the work. In the introduction to the book, the matter is put more formally. I have even sacrificed my notation, retaining the old formulae the better to show by example how irrational they are, and leaving to time the consummation of a reform which chemists have not yet adopted. Confusion continued to reign for some time longer. The terms equivalent, atomic weight, molecular weight were used and abused in every conceivable sense, sometimes even employed as synonymous. About the middle of the century, 2 units or standard elements were in use for the determination of combining weights. Dalton had suggested hydrogen as unity, and this standard was adopted by Gmelin and many others. Wollaston and Berzelius took oxygen as the standard, Wollaston giving it the value 10 and Berzelius using it as 100. Thomson had given it the value 1. The standard of Berzelius was the accepted one for a long time, but about 1842 a return was made to the standard of Dalton. It was in this year that Dumas, whose atomic weight determinations are classical, redetermined the ratio oxygen to hydrogen from the composition of water and had ascertained it to be 15.96 to 2, and had expressed his belief that the true value was probably 16 to 2. His number, which in the same year was confirmed by the results of Erdmann and Marchand, was for a long time considered as extremely exact. However, the work of Jean-Servais Stas, 1813 to 1891, soon after furnished numbers for the combining weights of a large number of elements which had all been determined by direct reference to 16 of oxygen, and the accuracy of which was far superior to that of the ratio oxygen to hydrogen. Indirectly, he had obtained for hydrogen in terms of oxygen equals 16.00, the value 2.02. Though not attaching special importance to this result, Stas asserted that the composition of water was not known with sufficient accuracy for hydrogen to be a suitable standard, and he expressed himself in favor of 16 of oxygen. Since, however, 16 was then generally accepted as the exact combining weight of oxygen in terms of the hydrogen standard, Stas' recommendation involved no recalculation, that is, no change in practice, only a change in theory desirable from the point of view of future possibilities. The adoption of the oxygen standard advocated would have meant that if a redetermination of the composition of water should lead to a change in the value of the ratio oxygen to hydrogen, the effect of this would only be an alteration of the value used for the combining weight of hydrogen, and not the necessity of a recalculation and a consequent change of all the combining weight values determined directly in terms of oxygen. Stas' suggestion, which it must be admitted was not pressed strongly, did not receive much support. All the work of Stas was monumental in the care taken to secure accuracy. The determinations of atomic weights by him of importance were those of silver, potassium, sodium, lithium, lead, chlorine, bromine, iodine, sulfur, nitrogen, and oxygen. Much of this work was carried out to prove or disprove the correctness of Prout's hypothesis, and Stas concluded as follows: I have arrived at the absolute conviction, the complete certainty, as far as it is possible for a human being to attain to certainty in such a matter, that the law of Prout, together with M. Dumas' modifications, is nothing but an illusion, a mere speculation definitely contradicted by experience. In 1860, J.C. Marignac, 1817 to 1894, who had determined the atomic weights of a number of elements, published a paper in support of what he termed Prout's law. He observed that the differences between the result obtained by M. Stas and those required by the law of Prout are certainly very small, but they are considerably greater than the greatest differences between the results obtained in each set of experiments. The results referred to, as well as those of Marignac himself, are appended. Silver, Stas, 1860, 107.943, Marignac, 107.921, Prout, 108. Chlorine, Stas, 35.46, Marignac 35.456, Prout 35.5, potassium, Stas 39.13, Marignac 39.115, Prout 39, sodium, Stas 23.05, Prout 23, ammonium, Stas 18.06, Prout 18, nitrogen, Stas 14.041, Marignac 14.02, Prout 14, sulfur, Stas 16.037, Prout 16, lead, synthesis of sulfate, Stas 103.453, Prout 103.5, lead, synthesis of nitrate, Stas 103.460, Prout 103.5. Marignac reasoned from Stas's results that Prout's hypothesis was substantiated rather than disproved. He employed the two arguments of the Proutians that Stas's numbers were very close approximations to whole numbers and hence could be considered as such, and that those approximations were too numerous to be accidental. This fatal error of rounding off fractions into whole numbers was the very thing which misled Prout at the beginning, and with him there was far more excuse for it. Marignac further said that should future determinations of other elements give similar approximations, he would feel assured of the existence of some fundamental cause which brought about the multiple relation of the atomic weights and subordinate causes which modified it. He thought that Prout's law deserved to rank with that of Gay-Lussac or of Mariotte. In another place, Marignac referred to Prout's law as one of those not absolute but only approximate laws, like many other natural laws. From 1888 onward, there appeared in quick succession redeterminations of the ratio oxygen to hydrogen, all demonstrating that Dumas's experimental number 15.96 was too high, but in the meantime Lothar Meyer and Seubert, strong champions of the hydrogen standard, had made this value the basis of very popular atomic weight tables. The new data did not provide a sufficiently reliable number to make recalculations of all the other values desirable, and the obvious way out of the difficulty, the use of the tables of Ostwald, in which the 16.000 oxygen standard was used, was not generally accepted. As a result, two tables of atomic weights, one based on O equals 16 and the other on O equals 15.96, were in use until quite recently. From the year 1896 onward, K. Seubert exerted himself to effect a general agreement with regard to the basis upon which all atomic weights should be founded, and in 1900 an International Atomic Weights Commission was appointed for the purpose of settling the question. The result of their deliberations has been to make oxygen, O equals 16, the official basis instead of hydrogen, H equals 1. The hydrogen unit is, however, often preferred still, both in practical work and in teaching. The main ground for the Commission's taking oxygen as the foundation is the fact, originally brought forward by Berzelius, that by far the greater number of the atomic weights have been derived from compounds of oxygen and not from compounds of hydrogen. Among the chemists other than those mentioned, whose efforts were directed to improving the methods of determining atomic weights, may be mentioned Turner, Penny, Marchand, Pelouse, Deville, and Scherer. Recently, Morley and Richards have done noteworthy work. The most recent table of international atomic weights is as follows. Aluminium, Al, 27.1. Antimony, Sb, 120.2. Argon, A, 39.9. Arsenic, As, 75.0. Barium, Ba, 137.37. Bismuth, Bi, 208.0. Boron, B, 11.0. Bromine, Br, 79.92. Cadmium, Cd, 112.40. Cesium, Cs, 132.81. Calcium, Ca, 40.09. Carbon, C, 12.00. Cerium, Ce, 140.25. Chlorine, Cl, 35.46. Chromium, Cr, 52.1. Cobalt, Co, 58.97. Columbium, Cb, 93.5. Copper, Cu, 63.57. Dysprosium, Dy, 162.5. Erbium, Er, 167.4. Europium, Eu, 152.0. Fluorine, F, 19.0. Gadolinium, Gd, 157.3. Gallium, Ga, 69.9. Germanium, Ge, 72.5. Glucinum, Gl, 9.1. Gold, Au, 107.2. Helium, He, 4.0. Hydrogen, H, 1.008. Indium, In, 114.8. Iodine, I, 126.92. Iridium, Ir, 193.1. Iron, Fe, 55.85. Krypton, Kr, 81.8. Lanthanum, La, 139.0. Lead, Pb, 207.10. Lithium, Li, 7.00. Lutetium, Lu, 174.0. Magnesium, Mg, 24.32. Manganese, Mn, 54.93. Mercury, Hg, 200.0. Molybdenum, Mo, 96.0. Neodymium, Nd, 144.3. Neon, Ne, 20.0. Nickel, Ni, 58.68. Nitrogen, N, 14.01. Osmium, Os, 190.9. Oxygen, O, 16.00. Palladium, Pd, 106.7. Phosphorus, P, 31.0. Platinum, Pt, 195.0. Potassium, K, 39.10. Praseodymium, Pr, 140.6. Radium, Ra, 226.4. Rhodium, Rh, 102.9. Rubidium, Rb, 85.45. Ruthenium, Ru, 101.7. Samarium, Sa, 150.4. Scandium, Sc, 44.1. Selenium, Se, 79.2. Silicon, Si, 28.3. Silver, Ag, 107.88. Sodium, Na, 23.00. Strontium, Sr, 87.62. Sulfur, S, 32.07. Tantalum, Ta, 181.0. Tellurium, Te, 127.5. Terbium, Tb, 159.0. Thallium, Tl, 204.0, thorium, Th, 232.42, thulium, Tm, 168.5, tin, Sn, 119.0, titanium, Ti, 48.1, tungsten, W, 184.0, uranium, U, 238.5, vanadium, V, 51.2, xenon, Xe, 128.0, ytterbium or neoytterbium, Yb, 172.0, yttrium, Y, 89.0, zinc, Zn, 65.7, zirconium, Zr, 90.6. Reverting to the middle of the past century, one finds that much of the credit of removing the difficulties attending the determination of the atomic weights and of transferring them to a more substantial foundation than had hitherto been in use is due to Stanislao Cannizzaro, 1826. It was he who, by his criticism in a paper entitled Sunto di un corso de filosofia chimica, Outlines of a Course of Chemical Philosophy, 1858, elucidated the methods employed for arriving at the relative atomic weights of the elements. He recognized as especially reliable the deduction of these values from the vapor densities of chemical compounds, a method now in universal use. Cannizzaro's paper began as follows. Point. Quote, "It seems to me that the progress of chemistry within the last year has served to confirm the hypothesis of Avogadro, Ampere, and Dumas concerning the similar constitution of gaseous substances, namely, the assumption that equal volumes of gases, whether elementary or compound, contain an equal number of molecules. But they by no means contain an equal number of atoms, the reason for this being that the molecules of different substances, or even of the same substance in the different states which it can assume, may consist of a different number of atoms of the same or of different kinds. In order to bring my pupils to this same conviction, I have let them follow the same path that had led me to it, namely, that of the historical examination of chemical theories. I begin by showing how, from a consideration of the physical properties of gases, together with Gay-Lussac's laws concerning the relation between the volume of a compound and that of its constituents, there has arisen, as it were, of itself, that hypothesis which was first enunciated by Avogadro and shortly afterward by Ampere. While expounding in detail the line of argument followed by these two physicists, I proceed to prove that it is not in contradiction to a single known fact, provided only that we do as they did. 1. Distinguish between the molecules and the atoms. 2. Avoid confounding the criteria for comparing the weights and numbers of molecules with those employed for ascertaining the weights of atoms. 3. Abandon the erroneous view that while the molecules of a compound may consist of any number of atoms, those of the different elements must consist of one atom only, or at any rate of an identical number of atoms." End quote. He then discussed molecular weight determinations and showed that the hypothesis of Avogadro was a guide in such work. His argument in favor of making the weight of half the hydrogen molecule the standard met with favor and acceptance. Turning from the molecule to the atom, Cannizzaro showed that the law of Dulong and Petit and Avogadro's hypothesis were a guide in the determination of the atomic weights. To quote further from his paper, quote, "We need proceed to the investigation of the composition of the molecules. Whenever the substance cannot be decomposed, it must be assumed that the whole weight of its molecules is composed of one kind of matter only. But if the substance is a compound, we analyze it and thereby determine the invariable ratio by weight of its constituents, and we then proceed to divide the molecular weight into parts proportional to those of the relative weights of the constituents, and thus obtain the quantities of the elements contained in a molecular weight of a compound, all of them referred to the same unit in terms of which all molecular weights are expressed. According to this method, I compile the table of molecular composition, which follows. Name of the substance: hydrogen. Weight of one volume, or molecular weight, referred to the weight of a half hydrogen molecule, equals 1. 2. Weights of the constituents of one volume or of one molecule, all referred to the weight of a half hydrogen molecule, equals 1. 2. Hydrogen. Name of the substance: oxygen. Weight of one volume or molecular weight, referred to the weight of a half hydrogen molecule, equals 1. 32. Weights of the constituents of one volume or of one molecule, all referred to the weight of a half hydrogen molecule, equals 1. 32. Oxygen. Electrified oxygen: 128. 128. Oxygen. Sulfur under 1.000 degree: 192. 192. Sulfur. Sulfur above 1.000 degree: 64. 64. Sulfur. Phosphorus: 124. 124. Phosphorus. Chlorine: 71. 71. Chlorine. Bromine: 160. 160. Bromine. Iodine: 254. 254. Iodine. Nitrogen: 28. 28. Nitrogen. Arsenic: 300. 300. Arsenic. Mercury: 200. 200. Mercury. Hydrochloric acid: 36.5. 35.5 chlorine, 1 hydrogen. Hydrobromic acid: 81. 80 bromine, 1 hydrogen. Hydriodic acid: 128. 127 iodine, 1 hydrogen. Water: 18. 16 oxygen, 2 hydrogen. Ammonia: 17. 14 nitrogen, 3 hydrogen. Arsenine: 78. 75 arsenic, 3 hydrogen. Phosphine: 35. 32 phosphorus, 3 hydrogen. Mercurious chloride: 235.5. 35.5 chlorine, 200 mercury. Mercuric chloride: 271. 71 chlorine, 200 mercury. Arsenic chloride: 181.5. 106.5 chlorine, 75 arsenic. Phosphorus chloride: 138.5. 106.5 chlorine, 32 phosphorus. Ferric chloride: 325. 213 chlorine, 112 iron. Nitrous oxide: 44. 16 oxygen, 28 nitrogen. Nitric oxide: 30. 16 oxygen, 14 nitrogen. Carbonic oxide: 28. 16 oxygen, 12 carbon. Carbonic acid: 44. 32 oxygen, 12 carbon. Ethylene: 28. 4 hydrogen, 24 carbon. Propylene: 42. 6 hydrogen, 36 carbon. Acetic acid: 60. 4 hydrogen, 32 oxygen, 24 carbon. Acetic anhydride: 102, 6 hydrogen, 48 oxygen, 48 carbon. Alcohol, 46, 6 hydrogen, 16 oxygen, 24 carbon. Ether, 74, 10 hydrogen, 16 oxygen, 48 carbon. From this it follows that all the different quantities of hydrogen contained in the molecules of the different substances are whole multiples of the quantity contained in the hydrochloric acid molecule. He defined the atomic weight as the weight of one atom of the element referred to the weight of the hydrogen atom taken, equals 1.00, or oxygen equals 16.00, and stated that it is determined by finding the least amount of the element present in the molecular weight of any of its compounds, which, if these are volatile, is the least amount present in 2 volumes of any of these compounds in the gaseous state. It is unnecessary that the molecular weight of the element be known, only the molecular weights of as many volatile compounds as possible, together with the composition of these compounds expressed as parts of the molecular weights. Chemists were thus taught to rely on Avogadro's hypothesis, all inferences drawn from which, Cannizzaro showed, are in complete agreement with all the physical and chemical laws so far discovered. He gave, as an application of Dulong and Petit's law, the following. The specific heat of copper in the free state confirms the atomistic conception of its chlorides based on analogies with the corresponding chlorides of mercury. Their composition leads us to the inference that they have the formulae CuCl and CuCl2, and that the atomic weight of copper is 63, a fact made apparent by the following relations. Cuprous chloride, ratio between the components expressed by numbers whose sum is 100, chlorine to copper, 36.04 to 63.96. Ratio between the components expressed by the atomic weights, 35.5 to 63 equals Cl to Cu. Cupric chloride, ratio between the components expressed by numbers whose sum is 100, chlorine to copper, 52.98 to 47.02. Ratio between the components expressed by the atomic weights, 71 to 63 equals Cl2 to Cu. But the number 63 for the atomic weight, when multiplied by the specific heat of copper, gives a product nearly equal to that of the atomic weight of mercury or of iodine multiplied by their respective heats. We get atomic weight of copper, 63, times specific heat of copper, 0.09515, equals 6. By the use of this law and Avogadro's hypothesis, an approximation to a correct table of atomic weights was obtained, and the road for the inception of the great natural law underlying them was opened up. Before the atomic theory was formulated, numerical relations were proposed by Richter, the founder of stoichiometry, between the equivalents obtained by him for the various bases and acids. This mathematical work served but little purpose beyond bringing the whole subject of his equivalents into some disrepute. Only a few years passed after the publication of the first tables of atomic weights before their interrelation became a subject of speculation and research. In 1815 we have Prout pointing out the strange fact of their close approximation to whole numbers and boldly rounding them off into such. If they were integral multiples of hydrogen, he reasoned, then this might be the primal matter and all elements made up of it. The multiplen fever quickly took possession of the chemical world, even of conservative, level-headed workers such as Berzelius. Enthusiastic support was given it by the English chemists especially, and when Berzelius afterward became its great antagonist, Thomson and others busied themselves in its defense. The newly organized British Association devoted its fresh energies to an examination into the condition of the various sciences and, among other inquiries, set on foot one as to the grounds for believing in what was then called, and has been often so called since, Prout's Law. The result of this inquiry was adverse to the law, and it would have been dropped, in all probability, had it not been taken up by Marignac, Dumas, and the French chemists, with certain modifications rendered necessary by the more perfect knowledge of the atomic weights. Meanwhile, a different style of numerical regularity had been brought to the notice of chemists. In 1817, Döbereiner first noticed the strange grouping of analogous elements into threes, or triads, as they soon came to be called. He said, according to Venable, noteworthy relations are revealed when one examines the stoichiometrical values of the chemical elements and compounds arranged in series. 1. Those most often found in plants have the smallest values and are the most abundant. The highest values are less widely distributed. 2. Those corresponding in many physical and chemical properties as iron, cobalt, and nickel have almost the same stoichiometrical value. 3. Compounds which have like equivalent numbers are almost alike in chemical constitution. End quote. For a long period following this paper, there was no further attention given to this question, but in 1829 Döbereiner published another paper, which appears to have been a result of the atomic weight determinations of Berzelius in 1825. He indicated that the atomic weight of bromine approximates the arithmetical mean of the atomic weights of chlorine and iodine, namely 35.470 plus 126.470 divided by 2 equals 80.970, considering H equals 1. Of this mean he stated that though somewhat greater than 78.383, the number actually found by Berzelius, it so closely approximates to it as to justify the hope that repeated accurate determinations of all the atomic weights involved will lead to a disappearance of any difference. He found similar relations for the alkaline earths, the alkalis, and for the group comprising sulfur, selenium, and tellurium, as shown by the equations. 356.019 equals calcium plus 956.880 equals barium divided by 2 is equal to 656.449 equals strontium. But experiment gave for strontium, regarding O equals 100, 647.285. 195.310 equals natrium plus 589.916 equals potassium divided by 2 is equal to 392.613 equals lithium. But experiment gave for lithium, regarding O equals 100, 390.897. 32.239 equals sulfur plus 129.243 equals tellurium divided by 2 is equal to 80.741 equals selenium. But experiment gave for selenium, considering H equals 1, 79.263. End of section 19. Section 20 of The Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in May 2018. The Science History of the Universe, Volume 4, edited by Francis Rolt Wheeler. Chemistry. Chapter 15. Atomic Weights and Periodic Law. Part 2. For more than 20 years, little was added to the work of Döbereiner, and no new ideas were advanced. This was in part due to imperfections in the determinations of the atomic weights, and ignorance as to whether they should be written as had been done by Berzelius, or many of them doubled, as was done by Gerhardt. Further, the whole question of atomic weights was in much doubt, and numerical speculations concerning them would have had little significance during this period. The first to continue the consideration of such triads was Dumas, who in 1851 called attention to the triads of Döbereiner and suggested that in a series of bodies, providing the extremes are known, the intermediate bodies might be discovered, and stated that a suspicion arose as to the possibility of the intermediate body being composed of the extremes of the series, and thus processes of transmutation might be hoped for. The next year, P. Kremers pointed out the existence of certain regularly ascending series among the elements, and in 1858 he followed up the old idea of triads, arranging the elements in the form of conjugated triads, thus lithium equals 7, natrium equals 23, potassium equals 39, magnesium equals 24, zinc equals 40, cadmium equals 112, calcium equals 40, strontium equals 87.5, barium equals 137. In these triads we have the following proportions: lithium to natrium to potassium as 7 to 23 to 39, as lithium to magnesium to calcium. Such close agreement was not found in every case, however, and in 1863 Kremers gave up the doctrine of triads. In 1853, J. H. Gladstone announced that he found the numerical relations between the elements to be of three varieties, namely, 1. The atomic weights of analogous elements are the same. 2. The atomic weights of analogous elements are in multiple proportions. 3. The atomic weights of analogous elements may differ by certain regular increments. He considered the doctrine of triads as partly a natural law. The following year, J. P. Cook published a study of these numerical relations. He stated that the triads broke up natural groups of elements, a fatal blow to the doctrine, and classified the elements into 6 series, in each of which the number whose multiples form the differences is different and may be said to characterize the series. In the first it is 9, in the second 8, in the third 6, in the fourth 5, in the fifth 4, and in the last 3. The elements were further arranged in series according to the strength of their electronegative properties, or, in other words, as their affinities for oxygen, chlorine, sulfur, etc. increased, while those for hydrogen decrease as we descend. Cook laid stress on the fact that his grouping demonstrated that the elements may be classified in a few series similar to the homologous series of organic chemistry. In 1851, John Mercer carried out this comparison with the organic radicals more fully, basing his work partly on that of Max von Pettenkofer, who, while engaged on the subject of the regularities in the atomic weights, made the following comparison. 1. The equivalents of the inorganic elements, which form natural groups, show among themselves such constant differences as the equivalents of organic compound radicals which belong to natural groups. 2. The simple inorganic elements can therefore be regarded from the standpoint of the compound organic radicals. Pettenkofer also criticized the doctrine of triads. Lenzen and Odling were about the last chemists to attempt to develop the doctrine of the triads. The former gave 20 triads, grouping the elements according to their chemical and physical characteristics. But this classification was unsatisfactory, and he suggested a division in dyads, the third member forming a binding member. For example, the triads potassium, natrium, and lithium became dyad potassium, natrium, and binding member lithium. The consideration of the numerical regularities of the atomic weights from the point of view of the homologous organic series, of which the ideas of Pettenkova form a good illustration, was also taken up by Dumas, who later published his view of double parallelism. He made this comparison. Nitrogen equals 14, phosphorus equals 31, arsenic equals 75, antimony equals 122, fluorine equals 19, chlorine equals 35.5, bromide equals 80, iodine equals 127. On adding 108 to the number for nitrogen, we obtain that for antimony, and on adding it to fluorine, we get iodine, and so the addition of 61 gives us respectively arsenic and bromide. These facts teach the propriety, he says, of arranging the metals in series that shall show a double parallelism, for such a classification brings to view the various analogies existing between these elements. None of these considerations materially advanced the subjects of triads from the state in which it had been left by Döbereiner. But, to quote from Freund's Study of Chemical Composition, when stress had once been laid on the approximate constancy of the differences in the atomic weights of elements forming a group, the ever-dominant desire for simplicity in numerical relations asserts itself. This led to unjustifiable attempts to alter the experimental values in order to make them agree with preconceived ideas. We know how variable and arbitrary were the criteria, prior to 1860, used in the determination of equivalent and atomic weights in general, but in the special cases of groups of elements there was more uniformity, hence the numbers obtained were comparable, and since the above considerations concerning classification applied only to groups of elements, it was possible to bring out within this compass a relation between atomic weight and properties. The extension to the case of elements in general soon followed. This was done in a set of short papers published from 1863 onward by Newlands, the forerunner of Lothar Meyer and Mendeleev. The work of Newlands followed immediately upon that of de Chamcourtois, who was the first to devise a symmetrical arrangement of the elements in his theory of the telluric screw. His first paper, 1863, considered some numerical relations between the atomic weights. To quote from Venable's Periodic Law, these relations were in part along the lines of the old triads. Thus, zinc was pointed out as the mean between magnesium and cadmium, copper between cobalt and zinc. In the group of the alkalis, one of lithium and one of potassium made two of sodium, one of lithium and two of potassium made one of rubidium, etc. Similar relations were observed for other groups. He also endeavored to show a certain kind of symmetry when the lowest member of a group was subtracted from the next higher member and when the lowest member of a triad was deducted from the highest. In a paper published in 1864, Newlands furnished a table containing the elements arranged in the order of their atomic weights. In a side column, the differences between these weights were given, each being deducted from the one next higher in the scale. The next year Newlands announced his law of octaves, which he deduced from his arrangement of the elements. He said in part that, if the elements are arranged in the order of their equivalents, with a few slight transpositions, as in the accompanying table, it will be observed that elements belonging to the same group usually appear on the same horizontal line. It will also be seen that the numbers of analogous elements generally differ either by 7 or by some multiple of 7. In other words, members of the same group stand to each other in the same relation as the extremities of one or more octaves in music. The same year he gave as an explanation of the existence of triads the fact that, in conformity with the law of octaves, elements belonging to the same group generally have numbers differing by 7 or by some multiple of 7. That is to say, if we begin with the lowest member of a group, calling it 1, the succeeding members will have the numbers 8, 15, 22, 29, etc. respectively. But 8 is the mean between 1 and 15. 15 is the mean between 8 and 22, etc. And therefore, as an arithmetical result of the law of octaves, the number of an element is often the exact mean of those of two others belonging to the same group, and consequently its equivalent also approximates to the mean of their equivalents. 2 years before the presentation of Newland's paper before the London Chemical Society containing the Law of Octaves, Lothar Meyer published the first edition of his Die modernen Theorien der Chemie, in which he gave a table of the elements arranged horizontally according to their atomic weights, so that analogous elements stood under one another, and the change of valence, along with that of atomic weight, could be easily observed. This was Meyer's first attempt, and his table exhibited less evidence of periodicity than that of Newland's, but it caused Meyer to give the question of the relationship of the atomic weights more serious consideration, and his mind continued working on the atomic relationship. His first table had been in the following form. On leaving Eberswald in 1868, he left with his successor the following elaborate table according to Seubert. The following year, Dmitry Mendeleev, 1834 to 1907, a Russian chemist, published his first paper embracing the important principles of the periodic law. He states that he was led to the consideration of the question in this way. When I undertook to write the textbook entitled The Foundations of Chemistry, I had to decide for some one system. Less in the classification of the elements, I should have allowed myself to be guided by accidental and, so to speak, instinctive reasons, rather than by an accurate and definite principles. Mendeleev then showed that the principles hitherto used in classification had not been of a quantitative nature, and he laid stress on the superiority of a system which is based on numerical relations, and therefore leaves no scope for arbitrary interpretation. Consideration of the numerical data available in the case of the elements led him to the rejection of the optical, electrical, and magnetic properties, because these vary with the conditions, and of the vapor density, because this is not known for many elements, and is different for the allotropic modifications. He next emphasized the unalterability of the atomic weight, stating that, "For this reason I have tried to take as basis for my system of classification the value of the atomic weight. Beginning with the one of smallest atomic weight, I arranged the elements according to the magnitude of their atomic weights, when it became evident that there exists a kind of periodicity in the properties of the simple substances. Hence, in this system of classification, the atomic weight of an element determines the place to be assigned to it, and all the comparative investigations that I have made lead me to the conclusion that the magnitude of its atomic weight determines the character of an element in the same measure as the molecular weight determines the properties and many of the reactions of a compound. I designate by the name of periodic law the mutual relations between the properties of the elements and their atomic weights, relations which are applicable to all the elements, and which are of the nature of a periodic function." Mendeleev's first table was very imperfect, and the scheme of arrangement he followed was not entirely according to the size of the atomic weights. It was according to this arrangement. He made use of other arrangements also, but the tables which he gave in 1871 contained a plan resorted to in its final and perfected form. One of these tables gave the horizontal and the other the vertical method of arrangement. These follow. These tables contain the periodic law as it is known to us. They have not been very materially altered, though they have been corrected in minor points. The work since has been mainly one of elaboration, and, as Venable observes, the credit for the expansion and filling out of the periodic law, its extension to the other properties of the elements, and the bringing of the various compounds of these elements into consideration also, has been almost entirely due to the skill and knowledge of Mendeleev. In 1870, Meyer offered a full table representing the nature of the elements as a function of their atomic weights, which was so similar to Mendeleev's that many accused him of plagiarism, but his claims to the authorship of the periodic law are based on his 1864 and 1868 tables, and his 1870 system appears to have been an expansion of his earlier tables. It is generally considered that Mendeleev and Meyer worked out the periodic law independently. The periodic law soon attracted merited attention, but for several years its importance was not generally recognized, and it was not until the discovery of some new chemical elements, thereby fulfilling certain predictions of Mendeleev, that it became accepted. Mendeleev had obtained the atomic weights of elements not fully investigated by taking the mean of the weights of what he termed the atom analogues. For instance, the atom analogues of selenium were arsenic and bromine on the one hand, sulfur and tellurium on the other. Its atomic weight should be 75 plus 80 plus 32 plus 125 divided by 4 equal to 78. He also had applied the periodic law to the determination of the properties of unknown elements. This was accomplished by estimating the physical and chemical character from those of the atom analogues, since he had established that all properties were functions of atomic weight. He described the properties of 3 undiscovered elements, and the following values he predicted will show why the periodic law was finally gladly accepted. Eka aluminium, suggested by Mendeleev. Atomic weight 68, specific weight 6.0, atomic volume 11.5. Gallium, discovered in 1875 by Lecoq de Boisbaudron. Atomic weight 69.9, specific weight 5.96, atomic volume 11.7. Eka boron, suggested by Mendeleev. Atomic weight 44. Oxide, Eka boron 203, specific weight 3.5. Sulfate, Eka boron 2, SO4, 3. Double sulfate not isomorphous with alum. Scandium, discovered in 1879 by Nielsen. Atomic weight 43.97. Oxide, scandium 203. Specific weight 3.864. Sulfate, scandium 2, SO4, 3. Double sulfate, 3 kalium 2, SO4, scandium 2, SO4, 3. Crystallizes in fine columns. The other, Eka silicon, ES equals 72, was discovered by Winkler in 1886. It is now called geranium, GE equals 72. At the present time, all chemists recognize the dependence of the properties of the elements upon the atomic weights, and the periodic law has become the central idea in the classification and study of the elements and their compounds. This law is the greatest discovery in chemistry since the announcement of Dalton's atomic theory, and has been much more rapidly accepted. It promises to lead up to results of the utmost importance. The close and mystifying relationship existing between the chemical elements which was revealed by the periodic law naturally has attracted the minds of scientists to thoughts similar to the conception of one primordial matter, as expressed by the Ionian philosophers, and later by Bacon, Descartes, and Boyle. To quote Freund, "Within the last 2 decades, experimental evidence, physical and chemical, has been accumulating in support of these speculations, and the last few years' contributions have been such as to make the complexity of the atoms as much of an established fact as that of the molecular and atomic structure of the masses of matter that we perceive. Moreover, the empirical results which, taken in their entirety, can almost be said to have proved this point, have also supplied evidence which justifies the course hitherto followed by chemists in assigning to the atoms a very special place in the scale of the complexity of different kinds of matter. It seems that the diversity of matter begins only with the atom, that while the component parts of a molecule A are not the same as those of another kind of molecule B or C or D, etc., the constituents of an atom M are identical with those of any other different atom P or Q or R, etc., that all atoms are compounded of the same one kind of primordial matter. The most important papers which have been published on the unity of matter and on the composite character of the elements are those of Sir William Crookes, Anton Grunwald, Gustav Wendt, Henry Wilde, Edward Moisel, W. Pryor, C. T. Blanchard, and Sir Norman Lockyer. Of these speculations and views, the most important is the hypothesis of Crookes. According to him, the chemical elements have resulted by gradual condensation from a primary material which he terms protyle. He arrived at this view in 1886 from observations on the phosphorescent spectra of the yttrium earths. When he advanced this hypothesis provisionally, Crookes had to assume the complexity of the elementary atoms, but since then, experimental and theoretical knowledge on this point has become more definite, as is shown by J. J. Thomson's investigations on the structure of the atom. Thomson started from the hypothesis that the atom is an aggregation of a number of simpler systems, and that these are formed by corpuscles associated with equal charges of positive electricity. He then traced the analogies between atomic structures and atomic properties, and furnished an explanation for the empirical relations between atomic weight and atomic properties embodied in the periodic law. As Freund remarks, in a section of the community usually referred to as the general public, there seems to be an impression that the recognition of the divisibility of the atom has dealt a death blow to that atomic theory which was founded by Dalton just 100 years ago. No misconception could be more complete. While nothing has had to be given up, nothing to be modified, there has been deepening of the foundations, extension of scope, correlation with other sciences. Except that some of the anticipations expressed have since been realized, the situation today is what it was when Kekule stated that while from a philosophical standpoint he did not believe in the actual existence of atoms, yet as a chemist he regarded the assumption of atoms not only as advisable, but as absolutely necessary in chemistry. End of section 20.
Section 21 of The Science, History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Warren Cotty, Gurnee, Illinois. The Science, History of the Universe, Volume 4, edited by Francis Rolt Wheeler, Chemistry. Chapter 16, The Development of Applied Chemistry. Analytical chemistry, That division of chemistry which treats of the methods of ascertaining the chemical composition of substances and mixtures, both as to kind, qualitative analysis, and quantity, quantitative analysis, has been an indispensable aid to all branches of chemistry, pure and applied, during their modern development, and has itself undergone considerable elaboration and perfection. In particular, analytical methods, both qualitative and quantitative, have been and are being continuously improved. The services of Boyle, Hoffman, Marggraf, Scheele, and Bergman in qualitative analysis have been mentioned, and it will be remembered that Bergman was the first to publish a system of qualitative analysis in the wet way. He laid a firm foundation for the methodical employment of reagents, and the methods of qualitative analysis now in use have been developed from his analytical course of procedure. Wilhelm August Lapidus and Johann Gottling contributed materially to the systematic arrangement of the analytical methods in use during the first decade. The former published in 1801 his Handbuch der chemischen Analyse der Mineralkörper, and the latter his Praktische Anleitung zur prüfenden und zerlegenden Chemie in 1802. Other works followed these, and analytical methods became known and improved. Qualitative analysis in the dry way has been perfected by the use of the blowpipe, an instrument which was originally employed for soldering metals, and which was first employed for testing minerals by Cronstedt and Engström. Bergman and Gahn studied thoroughly the deportment of various substances and reagents under the flame of the blowpipe, and their treatise on this important branch of chemical analysis was published in 1779. Berzelius, Haussmann, and Wollaston later became interested in this field, and Berzelius, who was notably instrumental in introducing the blowpipe into chemistry, published a treatise on the application of this instrument in 1820. More recently, the art of dry assay, dosimetry, was considerably advanced by the important flame reactions of Bunsen. His treatise, Flammenreaktionen, was published in 1880. After the preparatory investigations of Bergman, Klaproth, Van Quillen, and Proust, it was Berzelius who worked out new methods of quantitative analysis, thereby promoting the systematic development of this branch. He had shown great ingenuity and inspired his pupils, more especially Heinrich Rose and Friedrich Wöhler, with like powers. Rose and Wöhler extended the observations of Berzelius, and made analytical methods generally known by the publication of their treatises. The Handbuch der Analytischen Chemie of the former first appeared in 1829 and passed through 6 German editions and 3 French editions, while the Praktische Übungen in der chemischen Analyse of Wöhler, which was published in 1853, was translated into Russian, French, and English. The chief exponent and great master of analytical chemistry, however, was C. Remigius Fresenius, 1818 to 1897, who for over half a century devoted his life and labors to its extension. He collated and examined all methods formerly in use, and devised many new ones, but his greatest services were the establishment of the Zeitschrift für Analytische Chemie in 1862, and the publication of his Anleitung zur qualitativen chemischen Analyse in 1841, and his Anleitung zur quantitativen chemischen Analyse in 1846. These works have been published in numerous editions and translations since. Other chemists who have aided in the discovery of new tests, improved methods of separation and determination, and in the designing of suitable chemical apparatus for analytical operations are Liebig, Strohmeyer, Bunsen, Fremy, Turner, Scherer, Rummelsburg, Gibbs, Blomstrand, Maragnock, and Winkler. Classen's services in electroanalysis have been referred to. Volumetric analysis, That process in which the reagents are employed in solutions of known strength has been greatly developed during the last 70 years, and volumetric methods are much used in technical analysis, owing to the fact that no weighing is necessary after the standard solutions are once made up, thus saving considerable time. The quantitative analysis of gases was greatly perfected by Bunsen, whose researches in this direction began in 1838. Bunsen published methods of estimating various gases by absorption and combustion, which have required only slight modification since, but the qualitative analysis of gases has only lately been developed in a scientific manner. The work of Winkler in this connection has been important, and he and Hempel have improved the apparatus for gasometry and gas analysis and have generalized methods. The quantitative analysis of organic compounds has gradually developed from the observation that carbonic acid and water are products of their combustion. Lavoisier indicated the right path here, and his process was improved upon by Gay-Lussac and Thenard, Berzelius, Liebig, and more recently by Densted, Colley, and Hempel. The exact determination of nitrogen only became possible after 1830, when Dumas had devised his method. Other methods of determining nitrogen have been worked out by Will and Varentrop, and by Kjeldahl, whose method is extensively used in agricultural chemical analysis for estimating protein. Many methods for determining the halogens, sulfur, phosphorus, and other elements which occur less frequently in organic bodies have been worked out, and these have found extended application in forensic chemistry, hygiene, and agricultural chemistry. The beginnings of phytochemistry, the chemistry of plant life, can be traced back to investigations made at the close of the 18th century. Priestley, Saint-Pierre, de Saussure, and others were familiar with the fact that green plants under the influence of sunlight will remove carbonic acid gas from the atmosphere and decompose it. They were also aware of the fact that ammonia salts are of value in stimulating the growth of plants. Nicolas Leblanc having pointed this out at the end of the 18th century. Although the problems of plant life, the mode and manner of plant nourishment and growth, had engaged the labors of many trained observers for many years, yet even during the first 3 decades of this century, the belief was almost universal that plants, like animals, derived their nourishment directly from organic matter. This assumption found its chief advocates in Germany and France in Albrecht Thayer and Mathieu de Dambossé, respectively. In their opinion, inorganic salts, the importance of which could not be absolutely denied, acted merely as stimulants, and not as if they were essential to the growth of the plant. Indeed, Thayer held that the creation of earths in plants through their vital forces was possible. In this assumption, he followed the opinion of Schrader, who so early as the year 1800 imagined that he had proved by actual experiments the generation of the ash constituents of plants by the vital forces. J. G. Wallerius, a Stockholm chemist, had sought to lay a much more rational foundation for agricultural chemistry in 1761 in his Ackerbrukets chemische Grunder, when he made a comparison between the plant constituents and the constituents of the soil in which they grew. It was Justus von Liebig who demonstrated the falsity of the views of Thayer and Dambossé, and who entirely disproved the humus doctrine, as the theory held at that time was called. It was in 1840, after exhaustive investigations on the weathering of rocks, on the formation of soils, and on the effects of rain and the gases which rain holds in solution, that Liebig published his classic work on the application of chemistry to agriculture and physiology. In this, Liebig completely undermined the foundations of the humus theory and enunciated the following foundation principles of modern agricultural chemistry. 1. Inorganic substances form the nutritive material for all plants. 2. Plants live upon carbonic acid, ammonia, nitric acid, water, phosphoric acid, sulfuric acid, silicic acid, lime, magnesia, potash, and iron, Many need common salt. 3. Manure, the dung of animals, acts not through the organic elements directly upon plant life, but indirectly through the products of the decay and fermentative processes. Thus, carbon becomes carbonic acid and nitrogen becomes ammonia or nitric acid. The organic manures, which consist of parts of remains of plants and animals, can be substituted by the inorganic constituents into which they would be resolved in the soil. Practical field trials, carried out by governments and large landowners, proved the correctness of Liebig's deductions from his laboratory experiments, and the many investigators in this line since have come either directly or indirectly from Liebig's school. Liebig's conclusion that one must restore to the soil that which the removal of the crop had withdrawn, if one would prevent its exhaustion, is the basis of successful agricultural practice today. A French chemist, J.B. Boussingault, worked independently along similar lines to Liebig, and the services which he rendered in carrying out researches on the nutrition of plants by new methods were of great importance. Mention may be made here about nitrification in soils and the assimilation of free nitrogen by plants, the most important discoveries in agricultural chemistry of recent years. In 1849, Georges Ville, then director of the Agricultural Experiment Station at Vincennes, proved by actual experiment that certain plants assimilate free atmospheric nitrogen, but his conclusions were strongly disputed, being directly opposed to those of Boussingault and Liebig, and also to subsequent investigations by Laws, Gilbert, and Pugh in 1857. An important experiment bearing on the point and extending over many years was begun in 1855 by Herr Schultz of Lupitz in Altmark, Germany. He grew lupines on very poor soil, with the addition of non-nitrogenous manures only, and found that, notwithstanding this, the soil became richer in nitrogen year by year. The next step toward the solution of the question was the discovery in 1877 of the now well-known process of nitrification in soils by Schlossing and Muntz. This nitrification being the work of definite microbes, some of which have been isolated, while more recent work has proved that the direct assimilation of atmospheric nitrogen by leguminous plants is brought about by the agency of certain microorganisms, tuberculobacteria, originally present in the soil. Cultures of these specific bacteria are now prepared on a manufacturing scale, under the name of nitrogens, for application to soils naturally deficient in them. It only remains to mention as a factor in the present and future growth of agricultural chemistry the experiment stations and laboratories established now by the governments of every civilized country. In the United States, for example, there are at present 61 agricultural experiment stations, all in charge of efficient specialists, and many intricate problems of national importance have been solved. The large chemical industries and, in fact, all branches of chemical technology have been immensely developed during the 19th and 20th centuries, and the achievements of chemistry in the arts and industries have been stupendous and varied. During the modern chemical period, pure chemistry and applied chemistry have been constantly interactive, and the latter has profited immensely by the extension of the former, while pure chemistry, theoretical, inorganic, organic, and practical chemistry, has in turn been greatly benefited by the opportunities offered by the industries. The advancement of technical chemistry has been especially aided, however, by the development of analytical chemistry, which has allowed of a keen insight into the composition of the various industrial products, thereby leading to the introduction of many technological innovations. Then, too, industrial research has been and is being constantly fostered by chemical manufacturers, and this has led to the accruement of important novelties and improvements. The literature of technical chemistry is very extensive, but the standard treatises of Rudolf von Wagner, Handbuch der chemischen Technologie, Karl Kosmarsch, Geschichte der Technologie seit der Mitte des 18. Jahrhunderts, T.E. Thorpe, A Dictionary of Applied Chemistry, and Ernst von Meyer, A History of Chemistry, translated by McGowan, contains accounts of the development of the important industries. The manufactures of sulfuric acid and soda, which may be looked upon as the basis of all the other chemical industries, and which are naturally followed by those of hydrochloric acid, bleaching powder, chlorate of potash, and other salts of potassium, nitric acid, etc., only attained to their full vigor after the various processes involved had been explained by chemical investigation and after the most favorable conditions for those processes had been worked out. Important practical improvements were made in the manufacture of sulfuric acid so early as the beginning of the 19th century, e.g., the amount of steam required was regulated and the process was made continuous, the latter by Holker. The first attempt to explain this remarkable chemical process of the formation of sulfuric acid from sulfurous acid, air, water, and nitrous gas was made by Clement and Desormes, who recognized the important part played by the nitric oxide. How essential for the manufacture the careful observations on the chemical behavior of nitrous acid to sulfurous and sulfuric have been is sufficiently evidenced by the introduction of the Gay-Lussac and Glover towers to which they gave rise, and which have made the process into one complete whole. In 1831, Peregrine Phillips discovered the contact process by bringing about the combination of sulfur dioxide and oxygen in presence of platinum, but it was only 40 to 50 years later that Clemens Winkler converted this experiment into a technical manufacture. The contact process, in many modifications, has developed and improved so rapidly that many think it will eventually supplant the old chamber process altogether. Common salt forms the foundation of the soda industry, whose history commences with the beginning of the modern chemical period. Nicolas Leblanc was the first to succeed in converting salt into soda, with sodic sulfate as an intermediate product. Malherbe and de la Metherie, having some time previously attempted to utilize the latter substance in the same way, but without material success. It was in 1791 that Leblanc commenced the actual manufacture of soda, and in the year 1823 Musprat began the erection of his alkali works at Liverpool. His name deserves a foremost place in connection with the development of the soda industry. The formation of soda from the sulfate, by fusing the latter with coal and limestone, was ultimately so far explained by exact chemical experiments as to allow of a tenable theory of this fusion process being advanced. Scientific researches have also given rise to numerous important improvements in the soda manufacture, e.g. to the beautiful process of Hargreaves and Robinson, by which sulfate of soda is prepared directly, without the previous production of sulfuric acid, to the introduction of revolving soda furnaces, and to many processes for utilizing and rendering harmless the unpleasant alkali waste. But the greatest advance of all in this direction is the comparatively recent and exceedingly simple process of chance, by which nearly all the sulfur in alkali waste can be recovered at a very cheap rate. Purely chemical observations have also led to what was, until quite recently, the most important of all the innovations in the soda industry, the conversion of common salt into carbonate of soda, without the intermediate formation of sulfate at all, by the ammonia soda process. The manufacture of ammonia soda and of artificial manures has grown so enormously of late years that the demand for salts of ammonia has increased proportionately. But this requirement has, in its turn, been met by introduction of improved apparatus for the working up of gas liquor and by the successful attempts to extract the nitrogen of fuel in the form of ammonia, at the same time that the heat from the fuel or the residual coke is itself being utilized. Berthollet's experiments upon the bleaching action of chlorine and the chlorides of the alkalis led to the manufacture of the bleached liquor known under the name of eau de Javel. Chloride of lime was first produced by Messrs. Tennant and Company in Glasgow in the year 1779. Weldon's process for the recovery of the manganese dioxide, required in the preparation of chlorine, from the otherwise worthless chlorine waste has been in practical working since 1867. Deacon's method of producing chlorine directly from hydrochloric acid has never been very widely used. The manufacture of bromine and iodine is based upon the original work of Gay-Lussac and Ballard. Laboratory experiments have also led to the production of iodine from other liquors which were formerly looked upon as valueless, e.g. those from Chile saltpeter and from phosphorite after its treatment with acid. To A. Frank is due the merit of having made bromine available for technical purposes by preparing it from the mother liquor of the Stassfurt waste salts. Nitric acid plays an important part in chemical industries, especially since the development of the manufacture of explosives on a large scale. Potassium nitrate, which has been known and valued for so long, is still an indispensable ingredient of black gunpowder. Since the introduction of the nitrate of soda from the Chile deposits, nitric acid has been prepared from it, instead of from the more expensive nitrate of potash, by the old process of distillation with sulfuric acid, the latest advance here being the distillation of the nitric acid in a vacuum. The explosives, whose preparation now forms a great industry, have all been made available for practical use by chemical investigations. The epoch-making discovery of gun cotton by Schoenbein and Bachter independently in 1846 must be recalled here. Nitroglycerin had been known as a chemical preparation discovered by Sobrero for 15 years before it began to find extended application in 1862 as the result of Nobel's researches. The match industry owes its enormous development to the increased knowledge of chemical preparations and processes. There is a marked contrast between the chemical tinder of 1807, i.e. matches containing a mixture of chlorate of potash and sulfur, which were ignited by dipping them into sulfuric acid, and the present friction matches. Those prepared with ordinary phosphorus were most probably first introduced in 1833 by Arini of Pesch, and subsequently by Romer of Vienna and Moldenhauer of Darmstadt. They have since undergone many improvements, the most important of these being subsequent to the discovery of amorphous, not poisonous phosphorus, which had been used since the year 1848. Phosphorus has been manufactured on the larger scale for about 50 years. Scheele's process for its preparation was improved upon by Nicholas so far back as 1778, and has been materially modified in recent years. Closely connected also with the soda industry are the manufactures of ultramarine and of glass. The former substance was discovered in 1828 by Gmelin, and at about the same time by Guamet. A little later it was also discovered independently by Gotig of Meissen, who was the first to prepare it on a technical scale. The production of glass reached a high state of development in olden times through pure empiricism, but has greatly benefited by chemical research. The manufacture of glass with sulfate of soda and the improvements in flint and crystal glasses belong to the last century, while progress has also been made in silvering by Liebig and in glass painting through the discovery of new mineral colors. Water glass, which was known to Agricola and Glauber, was made available for technical purposes by Fuchs in 1818 and has since then been used for a great number of different purposes, e.g. for impregnating wood and preparing cements. The attempts to utilize raw vegetable products, particularly wood and straw, for the production of paper were first carried out in the year 1846. In caustic soda, a reagent was found by means of which cellulose could be prepared from these materials, while of late years a solution of calcium sulfite in sulfurous acid has shown itself especially well adapted for this purpose. The above process for the production of sulfite cellulose resulted from the chemical investigations of Tillman. Cross and Bevan's discovery that cellulose can be dissolved by carbon disulfide and soda, and thus be converted into a soluble cellulose xanthate, has enormously extended the uses to which the plastic material can be put. Objects of all kinds, from artificial silk to billiard balls, can now be made of pure cellulose. The beet sugar industry has developed into an enormous manufacture from experiments carried out by chemists on a small scale. Marggraf's discovery in 1747 that sugar was present in the juice of beet was not at that time capable of being applied commercially. Achard, a pupil of Marggraf, and others again took up at the end of the 18th century the problem of obtaining sugar from beet on the large scale, and they devised a process which was carried out in factories during the years of the Napoleonic Wars. However, this process was unable to exist, being a very imperfect one and giving but a small yield of sugar, and it is from the year 1825 that the real rise of the beet sugar industry dates, various factors entering into its growth, not the least of which was the practical application of chemical knowledge. Scheibler's strontia process for obtaining the crystallizable sugar from molasses is based upon a knowledge of the various saccharates of strontia. The filtration of the refined juice through bone charcoal was first recommended by Figuier in 1811 and then by de Rosny in 1812, and has since become an essential part of the process. The use of vacuum pans for evaporating the syrup was introduced by Howard in 1813, since which time many improvements have been made in them. Osmosis, which was first applied on the large scale by Damrenfalt in 1863 for extracting the crystallizable sugar from molasses, was developed by researchers in physical chemistry. The development of the fermentation industries has been immensely extended by chemical investigation, while at the same time the nature of the processes themselves has been explained. The latest work of E. Buchner and his pupils has resulted in showing that fermentation is brought about by an enzyme, zymase, produced from yeast. Among the more important observations in this branch during recent years are those of Affront upon the favorable effect of a minute quantity of hydrofluoric acid on the fermentation process, and of others upon the advantages gained by ventilation and by the use of pure yeast cultures. A knowledge of the normal composition of wine and beer has led to rational suggestions for the improvement of those liquors. It would be impossible to attempt even a bare enumeration of the more important innovations in this branch, many of which are due to Pasteur, e.g., the pasteurization of beer. In no other section of technical chemistry have there been so many discoveries made by systematic investigation as in that of artificial dyes. The first aniline dye which was produced upon a technical scale was the mauve prepared by W. H. Perkin in 1856 by acting upon aniline with bichromate of potash and sulfuric acid, and it was to him that the introduction of the color industry is due. A. W. Hoffman observed in 1858 the formation of aniline red, magenta, which was shortly afterward manufactured by another method by Verguin of Lyons, and introduced into commerce under the name of fuchsine. This was followed by the discovery of aniline blue, aniline violet, and aniline green, all of which were first prepared by Hoffman himself, while he proved that all of them were derivatives of fuchsine. The discovery of methyl violet by Loth in 1861, and that of aniline black by Lightfoot in 1863, were of great practical importance. In addition to this, new and improved methods for the production of rose aniline dyes have been discovered and developed, e.g., oxalic acid, formic aldehyde, and carbonyl chloride, are now used for the synthesis of diphenylamine blue, the new magenta, methyl violet, and allied compounds. The valuable dye, alizarine, was formerly prepared entirely from the madder root, but is now obtained from coal tar, this revolution having been brought about by Grob and Lieberman's successful synthesis in 1869 of alizarine from anthracene, a constituent of coal tar. Following alizarine, other derivatives of anthracene were prepared from the year 1880 onward. An immense industry, that of so-called chemical preparations, has gradually been developed on scientific lines from apparently insignificant beginnings, which had their origin in the work of the apothecary. Such preparations belong partly to inorganic and partly to organic chemistry. As instances of this, one may take the great increase in the production of silver salts, bromine, and iodine for photographic and other purposes, and the manufacture of numberless other metallic salts, e.g., thiosulfates, hydrosulfites, borates, and silicates, not to speak of newly introduced compounds like the peroxides of hydrogen and sodium, sodium persulfate and other persalts, and compounds of lithium, rubidium, vanadium, etc. The already imposing list of inorganic preparations is being continually added to. The manufacture of organic preparations is still more extensive. The various alcohols themselves, their ethers and esters, chloroform, chloral, iodoform, aldehyde, etc., are now all essential to the chemical manufactures and to medicine. The processes by which these compounds are manufactured are the result of scientific researches, old and new. From what has been said, it is seen that coal tar is the raw material from which many organic preparations are obtained, the technical importance of which it is difficult to estimate. Formerly a troublesome waste material, it is now of at least equal value to the other products from the distillation of coal. The manufacture of ammonia and salts of ammonia from gas liquor is now a thoroughly rational one, thanks to the careful chemical examination of the latter, and it forms a large and important branch of industry. The manufacture of coal gas was at first developed quite empirically, and it was only in the second half of the 19th century that improvements were introduced, which were based upon the scientific investigation of the relations existing between the composition of the gas and the mode in which the distillation of the coal was conducted, and this also applies to improved methods of purifying the crude gas. The present distillation process was introduced about the year 1880, after it was seen that by raising the temperature of decomposition, the yield of gas from pit coal was nearly doubled. In order to achieve the necessary white heat, gas retorts are now made from the most refractory fire clay instead of iron, and they are heated by regenerator gas. About 15 years ago, acetylene began to come into prominence as an important illuminant. Indeed, enthusiasts on the subject prophesied that the brilliant light which it gave would prove to be the light of the future. Produced from calcium carbide, a product of electrochemistry, it looked for a time as if acetylene were destined to become a formidable competitor of the electric light. The first impulse toward the use of furnace gas as a heating agent was given by the experiments of Faber-Diffar and of Bunsen, experiments made with the object of utilizing the gases issuing from the mouth of iron blast furnaces, which are rich in carbon monoxide. These, as well as the gases from coking ovens, were for long allowed to escape, and still are to some extent, but for the most part they now constitute important sources of heat. Lowe introduced water gas into technical use in 1875, preparing it by passing steam over red-hot coal. It is now much used for heating and illuminating purposes, and will undoubtedly become even more employed in time. The above resume of the development of industrial chemistry during the modern period will indicate how it has been elevated by a continuous infusion of scientific spirit, and manufacturing, once a matter of empirical judgment and individual skill, is more and more becoming a system of scientific processes. Quantitative measurements are replacing guesswork, and thus waste is diminished and economy of production ensured. In the United States, several decades ago, few industrial establishments furnished regular employment to chemists. But now, American manufacturers are becoming more and more appreciative of scientific research, and the results so far obtained have resulted in far-reaching improvements. In the production of a metal from its ores, or of indigo from coal tar, it is chemistry that points the way, and the more complex the problem, the greater the dependence. In devising new processes and in the discovery of new and useful products, chemistry is again the pathfinder. The community is apt to overlook the extent and diversity of the services rendered by the chemists, because of the quiet and unobtrusive way in which the work is carried out. The measure of a country's appreciation of the value of chemistry in its material development and the extent to which it utilizes this science in its industries generally measure quite accurately to the industrial progress and prosperity of that country. In no other country in the world has the value of chemistry to industry been so thoroughly understood and appreciated as in Germany, and in no other country of similar size and natural endowment have such remarkable advances in industrial development been recorded. And this, too, with steadily increasing economy in the utilization of the natural resources. Ex-President Roosevelt has well said, quote, "The life of the nation depends absolutely on the material resources which have already made the nation great," unquote. And M.T. Bogart recently has eloquently indicated how the chemist can and will be of service in that great problem, the conservation of natural resources. This work is not entirely that of the engineer, and, with the awakening of the producer and manufacturer to the value of science and industry, the outcome of the conservation movement can only be a successful one through the assistance of the chemist. End of section 21. Recording by Warren Cotty, Gurnee, Illinois. End of The Science, History of the Universe, Volume 4, Chemistry, edited by Francis Rolt Wheeler.